Oh, Peter, is it actually okay if you record?
Yeah, that's fine.
Yeah?
Yep.
Okay. And then this will go up on the YouTube page. Maybe. Let us know if that's okay to you. Otherwise, we can fix it up later. Okay. So it's my great pleasure to introduce today's speaker, Peter Schwindt. Dr. Schwindt is a distinguished member of the technical staff at Sandia National Lab. And there he leads research at the intersection of atomic physics and quantum sensing and biomedical applications. He got his PhD from the University of Colorado at Boulder under the direction of Dr. Eric Cornell in 2003. Then he was an NRC postdoc at NIST, where he developed chip-scale atomic clocks and magnetometers. And since 2006, he is at Sandia National Labs. One of his primary focus areas is the OPMs, the optically pumped magnetometers that he will be talking about, developing techniques to both miniaturize them and improve their sensitivity and bandwidth. And since 2007, he led a project to develop these OPMs for applications in MEG, which is magnetoencephalography, so magnetic fields originating from the brain. Also worked on many atomic clock projects, for example, developed an ytterbium ion microwave and optical clock, and focused on techniques for miniaturizing them and for getting low power consumption while maintaining excellent long-term frequency stability. He also led projects miniaturizing and extending the dynamic range of atom interferometers, accelerometers, using photonic integrated circuit-based laser systems. He holds several patents in atomic magnetometry, for example, one for an atomic magnetometer, which he co-invented with Cord Johnson. And more recently, he's also co-author on a patent for a multi-channel atomic magnetometer design. So this is all very cool stuff. It's about quantum sensing, very timely, and we are very, very happy that he's here and can tell us something about the state of the art in this lab. Thank you.
All right, thank you very much, Peter. And again, thank you for inviting me. Please let me know if there's any issues with audio or visual or whatever. Yeah, so should have got this up earlier, get a laser pointer up. Yeah, so talking about using optically pumped magnetometers or OPMs to measure the human brain is the main topic of research that I've been doing since about 2007. I've been working in this area. And so the work I'm going to present today was a contribution from many, many people, funded by the National Institutes of Health, and had the pleasure of a lot of collaborators. I really couldn't have done this without neuroscience collaborators, and being trained in atomic physics, I just didn't know anything about neuroscience. Maybe I still don't know much about neuroscience, but worked with Julia Stephen at the Mind Research Network, Samu Taulu at the University of Washington, iLabs, and then also Jim McKay at Can Do Systems have all been very helpful in me understanding the landscape of how to build an instrument that's useful for neuroscience researchers. And then I might also mention that my undergrad was at Evergreen State College, so I do have roots in Washington. I grew up in Washington, but now I live in New Mexico. All right. I want to just give you a brief intro to our group here at Sandia. So we do a lot of things in the area of atomic sensing or quantum sensing. As Peter mentioned, I've done a lot of work in atomic clocks, and at Sandia, I've really focused on buffer gas cooled trapped ion clocks. The topic today is about magnetometry. Done a lot of work in atom interferometry, specifically focusing on technologies to miniaturize them. So worked on photonic integrated circuits to develop the laser control required for an atom interferometer. And also here's a grating to make a grating magneto-optical trap, which has been fun to work on. My colleague Yuanyu Zhao does a lot of work in electric field sensing using Rydberg atoms for electric field sensing. And we also have a neutral atom quantum computing effort in our group. And then finally, as I was just briefly discussing with Peter before the talk started, is that we're doing some outdoor trace gas sensing work using dual comb spectroscopy and shooting lasers up from the ground to a tethered balloon so that we can measure the integrated path concentration of things like methane, CO2, water vapor along these various laser paths, which has also been really fun and interesting work. So just a flavor for our group, and anybody interested in a postdoc, let me know, because there's often opportunities in our group. And so if quantum sensing is your game or interest, please let us know. Okay, so the outline for my talk, I'll be introducing what magnetoencephalography is and optically pumped magnetometries. I'll delve into the physics some, and then talk about several measurements we've done with an older system that we've had for several years now, and talk about source localization of which neurons are firing and where inside the brain. And then also a brain-computer interface application where we're inferring the perceived speech of a person. And then finally, I'll talk about some new system development. And we're talking about building up our new OPM design and also scaling up. We hope to get up to 108 channels eventually. And then I'll conclude. Okay, so let me start out by discussing what is magnetoencephalography, or MEG for short. And so it's the measurement of the magnetic fields produced by neurons firing in the brain. And so let's talk a little bit about how that works. And so in a nerve cell, there's going to be ions flowing, which is an electrical current. And then that electrical current produces a magnetic field. So that's the signal that we're going after. In particular, we're looking at the electrical current in the dendrites. You might think that we would go after the current flowing in the axon, but it turns out the axon, that current flow, that the ions that flow in these channels, if you will, form a quadrupolar current flow. So the magnetic field produced by the axons is not very large. In the dendrites, the current flow is a dipolar current flow and has a large spatial extent, and therefore makes a relatively large magnetic field that we can potentially detect outside the head. So you have all these neurons. These neurons are generally organized so that current is flowing perpendicular to the surface of the cerebral cortex. And so if you have a whole bunch of neurons, about 10,000 produces a large enough signal to produce a magnetic field outside the head. So, we have a magnetic field that's circulating around a magnetic dipole that's being activated. A current dipole that's being activated inside a specific area of the brain. And so then you can have current dipoles that are activating throughout the brain. And so a lot of the work in magnetoencephalography is to go in and measure where this activation is happening. And then looking at a little more detail about the current flow. So we're going to have a primary current flow where we have a whole bunch of neurons firing simultaneously, which produces a current flowing through the dendrites and down the axons and then into the dendrites of the next nerve cells. And we generally call that the primary current, but there's also a return current, and that return current flows kind of throughout the cerebral spinal fluid inside the brain. And so we measure both this primary current and the return current inside the brain. That current then produces a magnetic field that we can measure outside the head. Now, the current will also produce an electrical potential, and you might have heard of EEG, or electroencephalography, which is a much more commonly used technique for measuring what's going on in the brain. And that's generally you put electrodes on the head and you measure the electrical potential between those electrodes, and that also gives you a measure of what's going on in terms of the currents flowing and the voltages required to push those currents through the neurons. But you might see these electric field lines have this distortion, and that's due to the low electrical conductivity of the skull. And so that distorts the electrical potential that one can measure on the head. And so you can't get as good spatial information out of the electric field. And that's really what motivates doing MEG, because the magnetic field simply passes through the skull without any effect. And so you get a much cleaner measure of the magnetic field. Okay, so what are some of the uses of magnetoencephalography, and the main clinical application of magnetoencephalography is the pre-surgical localization of epileptic foci. So a person with epilepsy will have generally have low-lying electrical activity related to the epilepsy, and and if epilepsy cannot be treated by pharmaceuticals, then you want to go in and do surgery and resect part of the brain, and you want to localize where this focus, or if there's multiple foci, you want to go in and remove that part of the brain, and you want to localize where that's happening before you go do that. And so the gold standard is to use like nets of electrode that you lay directly onto the brain. So you open up the brain, lift the skull back, and lay these nets of electrodes down, and then you can then localize where things are happening. It'd be great if this could be done non-invasively, because this generally you have to have the brain open for a day or so to get enough data to really localize where things are happening. So if you could do this in some sort of non-invasive, say a magnetoencephalography technique, that could be revolutionary for these patients, not to have to sit around for a long time with their brain open to the air. So that's one application where people are working now to try to figure out how to use MEG to do this. The other main applications of MEG are just kind of general neuroscience studies, studying the normal and diseased brain, looking at brain networks, looking at how different parts of the brain communicate with each other, because you can see when one part activates, then later on another part will activate it. So this is kind of called functional connectivity within the brain. And so there's a whole host of neuroscience work that's going on using magnetoencephalography. Now, as I already mentioned, EEG, but there are several other functional neuroimaging technologies out there to measure activity of neurons in the brain. And so I have three listed up here as probably the main three that are used for neuroscience research. And so it's EEG, MEG, and fMRI. And so fMRI is functional magnetic resonance imaging. And so fMRI, what that does is it doesn't directly measure neural activity, but measures blood flow, and essentially where is oxygen being consumed in the brain, and that's a proxy for neural activity. And so it's not a direct measure, and because it's not a direct measure, it has relatively poor time resolution, but its spatial resolution, as everybody knows from a beautiful MRI image, that the spatial resolution is quite good, down to the millimeter scale. And even though it's relatively expensive, it is widely used. I think the most functional neuroimaging studies, the most papers out there are based on fMRI, and that's largely because most MRI machines can be used for fMRI, for functional neuroimaging. And so there's this is a very popular technique, but there's definitely good motivation for going after EEG or MEG because of the very good temporal resolution. So this gives you a better idea of how networks interact because of the good time resolution, and you're directly measuring the neural activities, and you don't have this proxy. But EEG, as I mentioned before, the spatial resolution is relatively poor, kind of centimeter scale. MEG is better, down into the millimeter to centimeter scale, because you don't have this distortion to the skull. Today, this is what a squid-based system looks like. There's a person sitting here with a cryogenic dewar over their head, essentially. And so that's a relatively expensive machine. And so one of the motivations for studying optically pumped magnetometers is to see if there's a way to reduce cost. And then finally, there's another technique called functional near-infrared spectroscopy. And with this technique, you're able to shine light into the brain through the skull. This is near-infrared light, around 900 nanometers or so. And again, you can get a measure of the blood flow and the oxygen consumption in the blood, in the brain. And so this is a pretty interesting technique because it's relatively inexpensive, it's wearable, and so it's seeing some quite a bit of use these days as well. Okay, going back to magnetoencephalography, what are the field strengths we're looking at? And so Scott Seltzer's thesis out of Princeton had this nice diagram that I stole from his thesis. And so the Earth's field's sitting up here in the microtesla region, about 50 microtesla. The human heart, the magnetic fields just outside the chest, are around 100 picotesla, and the brain is around 100 femtotesla. So, you know, we're looking at essentially 9 orders of magnitude smaller magnetic field than the Earth's magnetic field. So that means you need a quite sensitive magnetometer to measure what's going on if you're measuring just outside the head. And for years, the main technique has been to use these low temperature superconducting quantum interference device magnetometers, or SQUID magnetometers. And they have a sensitivity operating around, 1 femtotesla or so. And the type of magnetometer I'll be describing today is called a surf magnetometer. And these can reach sensitivities below 1 femtotesla. And if you do a really good job with squids, they can also reach down below a squid, or below a femtotesla as well. But you'll see in my talk that the devices we're building, we're operating at a few to several femtotesla per hertz down in this level here. Okay, so kind of the pre-talk question was why use OPMs if squids are already out there? And there's a couple of reasons for that, for us developing a new type of sensor. And so one is the fact that, so here's kind of a schematic diagram of a squid sensor showing that you have liquid helium and you're holding your sensors at around 4 Kelvin. And you have to have a lot of insulation to make sure all your helium doesn't boil off and you don't cryogenically burn the person, the human subject. And that creates a fair bit of standoff. And so you're looking at least, 30 millimeters of standoff. And if you have someone with a smaller head, say a child, then the standoff can be larger because these are fixed helmet devices. But if you go with an OPM, you kind of have the opposite problem. Temperatures are around 150 degrees Celsius, but that's a much easier problem to solve. And you can also individually package these sensors and bring them closer to the brain. And so you can have a cortex to sensor standoff that's half. And if you think about a magnetic dipole, how that falls off, if you're 2 times closer, you're getting 8 times more signal. So you can really improve the signal size of your fields that you're measuring by getting closer to the brain. And then going back to like a person with a small head, say a child or an infant, then you can bring these sensors right up to the surface of the head. And you can make the array much more conformal to the head as well. So this is leading to some new applications, and the field has really exploded over the last decade and a half. And so here's a picture from the group at University of Nottingham showing the squid and an early OPM system where we have some OPMs in a 3D printed mouth that's attached to the person's head. And with this device, you can stand up, you can move around. So it's, leading to new paradigms where people can move. This group made a video of where they were measuring the brain of 2 people, where they're playing ping pong, tossing a ball back and forth between them, or hitting a ball back and forth. So it's pretty interesting and pretty exciting to see what's going to happen in this field over the coming decade. So talking about some of the early work, this was started out at Princeton using OPMs for MEG. And they made this big system where you had a large vapor cell. And so this really wasn't of a configuration where you could place it, surrounding the whole head. And so in 2007, we started a project to make a more modular sensor. And so this is a picture of me with our early sensor that we were able to publish back in around 2010 or so. And then NIST in Boulder made some pioneering work, really miniaturizing these sensors, getting down to the kind of just the individual sensors around a centimeter in dimension or so. And this work has now moved into a company called Fieldline. The first company on the scene, though, was QSpin, and they developed some compact magnetometers as well in 2013, and they were able to show some MEG signals with those early devices. And now this field, as I mentioned, is really growing, and there's a number of companies in this field And here's to name a few: Circumagnetics, Mag4 Health, and XMEG Tech is a company in China, and there's several others in China as well. So China has really taken up this technology and is developing this area as well. Okay, so that was kind of some introductory material about the field of magnetoencephalography and the use of OPMs in it. Now I'll transition into talking about some of the physics of OPMs. And so just to give some background here, there's three main physical effects. We're looking at the atom magnetic field interaction that goes by a couple of names, either the Zeeman effect or Larmor precession. There's the atom light interaction, and there's optical pumping, and there's in our device we also use the Faraday effect or Faraday rotation. And then there's going to be several different kinds of decoherence effects that scrambled up the atomic spin polarization. And so overall, what we want to be able to do to, say, model this OPM, how it works, we use a block equation to do that. And so we look at the atomic polarization or the atomic spin and how that evolves in the presence of a magnetic field and optical pumping. This ROP refers to optical pumping rate. And then also several decoherence effects as well. So this is a picture of the block sphere. In our device, we often have a pump laser. And then there's a magnetic field we're trying to sense. And so we'll pump the atoms along the z-axis, and then the field will cause the spins to precess about the direction of the magnetic field. So tip the spins over, and we want to get a sense of this angle that the spin polarization is making relative to our optical pumping direction. And that can give us information then about what the magnetic field is. And so this equation is a little dense to look at, so I'll go through this in a little bit more detail. But first, I want to give you kind of a picture of what's going on. I guess I forgot to mention that often there'll be a pump and a probe laser. Our device has a probe laser, but the video I'm about to show you only shows the pump laser. And so this was made by my colleagues up at NIST. And so this gives you a flavor of what's going on. So you have a vapor cell, a glass cell that has rubidium vapor floating around in it. And then you have individual rubidium atoms. Each rubidium atom has a spin associated with it. And then zooming a little bit more, then look at an individual atom and how that spin behaves. If you bring in circularly polarized light, that'll orient the atomic spin polarization along a particular direction. A magnetic field will cause precession of the field. And it's this angle relative to the pumping direction and the spin that we want to measure. And then with the magnetic field and the change in angle, the amount of light transmitted through the atomic vapor ensemble will change. And so as the magnetic field turns on and off, that modulates the intensity of the light coming through the atomic vapor. And so that's one way to measure how an OPM is measuring or senses of a magnetic field, is by measuring the amount of light transmitted by that pump laser. Okay, let's look at these different effects in a little bit more detail. So the rubidium-87 ground state is shown here, and all the energy levels associated with it. And here I'm trying to illustrate the atom magnetic field interaction, or the Zeeman effect. So here we have the F=1, F=2 ground state of rubidium-87. There's several Zeeman sublevels within each manifold. And then as a magnetic field is applied, these energy levels split apart. And so, and that's the Zeeman splitting. And so the splitting is proportional to the amount of the magnetic field that the atoms are experiencing. That's what we're going after. You know, the atomic clocks, most atomic clocks out there actually use rubidium-87. And that uses this hyperfine splitting, the zero MF=0 state here, and directly measures this hyperfine splitting because it's a very stable set of energy levels, and it's not perturbed by a magnetic field to first order. So getting back to our block equation, the block equation which represents, or the part of the block equation which represents the Zeeman effect, is this cross product here between the magnetic polarization, or sorry, the atomic polarization and the magnetic field. And this is very similar to the behavior of a top processing in the Earth's field. And so if you've ever solved that problem in classical mechanics, basically the same physics are happening for a magnetic field or for the atoms processing inside of a magnetic field. And the gyromagnetic ratio then is going to be given, or for rubidium-87 is about 2 pi times 7 hertz per nanotesla. Okay, now looking at the atom-light interaction, one of the main things we have to do to prepare the state of the atom to measure a magnetic field is to do optical pumping. And so going back and looking at the energy level picture, and here I'm just showing 2 MF sublevels in a ground state. And so you will generally start with the atomic ensemble equally distributed between both sublevels. And then if you apply circularly polarized light, that will drive a transition that depopulates this state. And then spontaneous emission will go back to both states, but since you're continuously driving out of the -1/2 state, the atoms will accumulate in the +1/2 state. And we represent this process in the block equation here by this optical pumping rate times the polarization vector of the light, circular polarization vector of the light. And and then if a magnetic field is applied in this picture, what we'd see is atoms being transferred back into the -1/2 state and then start to absorb light again. And so that's where this decrease in transmission occurs, is when a magnetic field is applied, you get this transition back to the other states and causing absorption again. Okay, and then there's multiple decoherence effects that we have to think about when we're dealing with these atoms. And they're flying around in the vapor cell at some 300 meters a second, colliding with the cell walls, colliding with themselves. And so we got to characterize all these and measure what these, how strong these effects are. So one effect that we call spin destruction is an atom-atom collision, rubidium-rubidium collision that randomizes the spin. There's another decoherence effect called spin exchange, where angular momentum is conserved. This can be a strong decoherence effect, but in our magnetometer, this turns out not to be a decoherence effect, and I'll explain that on the next slide. And then there's another set of spin destructions collisions because we put a buffer gas inside the vapor cell, typically nitrogen, and rubidium nitrogen collisions also cause spin destruction. So these two spin destruction terms are wrapped up into one total spin destruction rate, and that's overall depolarization of P here, or the atomic polarization. Another effect is diffusion. And so if atoms are colliding with the walls of the cell, they get completely depolarized. And so we need to take that into account as well as another depolarization rate. And then finally, the absorption of light. If light is absorbed by the atoms, that causes depolarization. and so we represent that by showing this optical pumping rate, spin polarizes, but it also causes a depolarization as well. So we represent that with this term. And then the RPR here, or R probe, is a rate associated with depolarization from probing the atoms with a probe laser. So these are the main effects that go into it. But now I want to address this spin exchange term and why we don't see that. And so we operate in this regime called spin exchange relaxation free regime. And so in this case, in a high field regime, spin exchange is very strongly depolarizing. And so I'm trying to color code the atoms here a little bit. So atoms in the F=2 level are green, and atoms in the F=1 level are red. And then you'll note that the gyromagnetic ratio is opposite for both of these levels. And so they'll actually process in opposite direction if atoms get transferred down between the states. So we start out with the atoms, say, in the F=2 state. And that's what I'm trying to represent here, this green circle with a magenta arrow going through it. And so atoms will process if they're in a high field regime, and then they will collide and undergo a spin exchange collision. And they might flip then their state from the F=2 to F=1 level. And that means they'll precess in the opposite direction. And so with this opposite direction precession, they will very rapidly begin to point in different directions, and the whole ensemble will depolarize quickly. And if you look at the ensemble average, you know, the macroscopic polarization will decrease very rapidly. But if you're in the low field regime or the surf regime, you have a single atom and it undergoes multiple collisions. You'll first precess one way, it'll collide, it'll precess back a little bit, it'll collide again, it'll start precessing in the original direction. And so you get this slowed down precession rate, but you don't get an overall decoherence. And so your ensemble average sticks around for a much longer time. So your coherence sticks around for a much longer time. And so operating in the surf regime, people have been able to demonstrate very sensitive magnetometers. The record, I believe, still is the record of around 160 attotesla per root hertz. And then a small scale magnetometer has been shown to operate down into the 5 femtotesla per root hertz in this kind of a 6 cubic millimeter vapor cell. And so looking at these cross sections, why this is so effective, when we compare spin exchange to spin destruction, the relative cross sections are about 3 orders of magnitude separated. And so that's why you get a dramatic increase in coherence time and therefore sensitivity for the magnetometers. Now you have to be in this low field regime. To be in the surf regime, you got to be in this position where spin exchange collisions are happening much more rapidly than the precession rate. But as you transition up out of that regime, you'll see the resonance line width, the magnetic resonance line width, go from something very narrow to something that's 2 or 3 orders of magnitude larger, depending on the temperature of the system. This can't be really wrapped up in a block equation very easily, not without major modification, but you can do a density matrix analysis. And if one goes up and looks these papers up, you can see some analytical results that show how you can model this curve here from going from low field to high field regime. Okay, so that's a very quick background of optically pumped magnetometers. Wanted to go into a little bit more detail about our specific approach to building the OPM. And so we're going to take advantage of the fact that there are 2 resonances close by in the rubidium atom, one at 795, one at 780, called the D1 and D2 line, respectively. And so in our magnetometer, we're going to use the D1 line to do optical pumping. So it'll be circularly polarized. We'll spin polarize all the atoms inside of our vapor cell here. And then we'll add in a second laser, also collinear with the pump laser. So this probe laser we'll use for detection. And so this is going to be linearly polarized. It's going to be, so here we're going to use the off-resonant Faraday effect and watch the polarization of the light rotate it as it goes through the polarized atoms. And so this will be the output of our magnetometers by observing how much the polarization of the probe laser rotated. And then how do we kind of do this collinear business? We use a multi-order wave plate so that it's a quarter wave plate at 795 and a half wave plate at 780. So we can get circular polarization and linear polarization with these 2 collinear lasers. And then we'll use a bandpass filter, so we only analyze the 780 nanometer light. By having a separate pump probe laser, we're able to optimize both lasers well and get a little bit more sensitivity out of our device rather than just measuring the pump laser directly. Okay, to measure a magnetic field, say we're trying to measure the field component in and out of the plane. And so to measure that, to set the sensitive axis, we apply a modulation that's oscillating in and out of the plane. And so using that oscillation, then we can do lock-in detection to measure the field component that's parallel to the B1 field. And so we do make a vector magnetometer in this way. And so if we then measure, go ahead and do the measurement and set everything up, these are what our signals look like. Without adding that B1 modulation, we have this magenta line as we scan the magnetic field. And so we get this nice narrow resonance that's about, you know, kind of 50 nanotesla wide or something like that. And and then the red tracer here is showing that raw data output of the magnetometer, looking at the Faraday rotation signal. And when we add that modulation, it looks like the red trace. And then when we do the lock-in demodulation, we get the blue trace. And so we're able then to measure on this very steep slope then how the magnetic field changes around zero field. And so, you know, we also call the surf magnetometer a zero field magnetometer because it operates best right at zero field. Okay, so let me jump in now to some of the applications. Clearly, I spent too much time on the first part of my talk. So when we put it all together and make a sensor, it looks something like this. We have light coming in, and on a single mode polarization maintaining fiber, we have a direct optical element that splits the beam into 4. So we have a rather large vapor cell, about 1 inch on a side. And we have 4 beams that are going through the vapor cell. And then the light's reflected back onto into our balanced polarimeter here. And so we have 4 separate photodiodes on each side here that we subtract to get a balanced polarimeter out, so we can measure that Faraday rotation of the atoms inside this cell. These early sensors had about 600 torr nitrogen inside the vapor cell. And the beam diameter is 2.5 millimeters. So we're measuring kind of a 20 millimeter volume. We're integrating the magnetic field over a 20 millimeter volume inside the vapor cell, and then the head would sit out over here. Here's a picture of the device. We have our fiber coming in here, our vapor cell here, and around the vapor cell, we have some on-sensor coils to apply these magnetic field modulations. Okay, so we take that sensor, we put it into an array inside of a person-sized magnetic shield. And so here's a picture of me getting ready to go inside with my colleague Amir Borna. And then we have lots of control systems around it. We have our laser system to drive the magnetometer. We have our data acquisition. We have to have a computer to stimulate the person as well, give them some stimulation that we can measure with our system. And so when we put this system together, here I'm showing a picture where we had 6 sensors giving us 24 channels, because we have 4 channels per sensor. And it's partially covering the left hemisphere of my head here. And so then we can do a couple of different experiments. So one is to apply some electrodes to the wrist and cause the thumb to twitch. And then by doing that, that activates the somatosensory cortex in the or I guess in about this region of the brain. And then you can start then averaging multiple stimuli together to get enough signal noise to see what's going on with these brain responses. And then you can do the same thing by putting a tone in the ears of a subject. And so here we're putting like a 1 kilohertz beep into the person's ear. And then again, you can see some response that's centered around the auditory cortex, which is located just above the ear. And so what we want to do is be able to localize where things are happening. And so we'll go, you know, we have this time trace, and then we'll say, okay, I want to localize things at the maximum here, maximum amplitude peak. That's about 20 milliseconds for the somatosensory stimulation, and at 100 milliseconds for the auditory stimulation. And so we make a magnetic field contour map, and then we invert that to identify a location inside the brain. And so that's what we're showing here. This is for the somatosensory evoked field. And so we're able to localize activity occurring in the somatosensory cortex. We can do the same thing with auditory data as well. And so over 3 subjects that are ID'd here, and these 2 different stimuli, so 6 different trials, we're able to localize where things are happening and compare it to a same measurement in a squid system, and we can kind of measure the localization error relative to these 2 systems. And we're able to get that error down below 1 centimeter for across all subjects. So that's really nice to see. Another thing of note is to show that the OPMs typically have a higher signal to noise ratio than the squid. And that's just because of the fact that we're closer to the head, even though our sensitivity is somewhat worse than the squid system. Okay, so one other application I wanted to mention is our attempt to use our OPM system as a non-invasive brain-computer interface. And we're trying to measure or imagined or covert speech. Particularly, we focused on perceived speech in our first efforts here. And so we're trying to develop an algorithm so we can do this non-computer interface to decode what the brain is sensing. And so again, showing some kind of gross pictures of the brain again. So this is other ways to do it. I showed the net of electrodes previously, but also there's been a lot of work in making these very high resolution arrays of electrodes that are actually pressed into the head. So these needles are pressed into the brain to kind of get single action potentials measured from single neurons. And once again, we're looking to say, all right, can we do non-invasively what's being done invasively? I mean, the shorter answer is no, we're not able to do as well because you get so much more information out of the direct measurement of the brain, but you still can do some interesting things. And so in this experiment, the person listened to a sentence, we measure the brain, we process the signal to reject some noise, and then we kind of lined up the data to extract some features that we could then put into a machine learning algorithm to see if it could then decode what the person was hearing. And so we're trying to measure what the subject perceived directly from the brain signal. And so we're using typically a convolutional neural network to try to decode what's going on. And so very briefly, can just show some of the results here. And so here we have the results for 5 different sentences. And with these 5 sentences, we're able to be very accurate, be able to tell the difference after being able to train the data on a few hundred times that the person listened to this, to the sentences, and then you have another set of the data that you're trying to decode from. And so we're able to do this with quite high accuracy. And one of the sentences wasn't quite as high as it should be, I guess. But as we go to more sentences, 10 sentences in this case, the first 5 sentences, we're still able to have relatively high accuracy. But in the next 5 sentences, we aren't doing so well. In particular, this sentence here, number 5, is always be getting confused for sentence number 8. Nevertheless, kind of the overall average is greater than 80% accuracy decoding for a single trial, which is pretty amazing given the kind of bad signal noise ratio that you have when measuring these brain responses. So, this is pretty exciting for us. And so we're looking to now move from this closed vocabulary. We'd be very much interested to move towards open vocabulary. Okay, so the final section of my talk is about our new system development. So let me jump into that. So in this new system, we're trying to build up to a full head array rather than just measure on the side of the head. We're trying to move into a system where we can do more paradigms, and this means going into a magnetically shielded room. We're also, redesigning our sensor to get some more performance, make them simpler to manufacture, and hopefully improve the overall reliability. And then at some point, we hope we can demonstrate a wearable array, but mainly what we're going after is improved spatial resolution. So I guess I better go through this pretty quickly, but we are implementing some design changes. Our new Gen 2 design changes the optical layout somewhat. So rather than having the photodiodes close together, we found we had a lot of crosstalk between channels when we did that. And so here we're going to a design that allows us to have individual detection with virtually no crosstalk between channels. So there's a few more details on the design. This is a CAD model of the design here. And so again, we have a diffractive optical element that splits the beams out. And so we're measuring these 4 different regions of the cell. And here's our balanced polarimeter. Some notable changes are that we reduce the beam size somewhat. We reduce the nitrogen buffer gas pressure. And because of that, we're able to reduce the temperature to get the same optical depth. And operating now instead of 145 C, around 130 C. And overall, then we're able to reduce the optical power, and both reducing the temperature and reducing the optical power for the pump and the probe is very important for us as we try to go to a larger array. Again, here's a picture of the sensor. It's about this long or so, 8 inches long or so. And, sensor heads or the vapor cells over here and the fibers coming in on the side. The bandwidth of these sensors is about 100 hertz. And we're also able to show that we can get about a factor of 100 gradiometric subtraction between adjacent channels. And so that's useful for canceling external noise. And then, looking at the overall noise performance, if you look at the magnetometers by themselves, they're around 10 to 12 femtotesla per hertz. And that's limited by both the magnetometer and also kind of the environment that we're in. And if we do gradiometric subtraction, we're around 5 to 6 femtotesla per hertz, between kind of 10 and 50 hertz. If we compare that to our Gen 1 sensors, they're about the same performance, but you'll notice the gradiometric noise in our Gen 1 sensors was a little bit better because we had more atoms participating in the measurement. But, over the years, we've been doing better at getting rid of technical noise, so the magnetometer noise is actually somewhat better in our new sensors. And then if we've built 18 of these sensors so far, so that's 72 channels, and we look at the histograms of the performance, the gradiometrically inferred sensitivity is between 5 and 6 femtotesla for most channels. And our bandwidth is sitting around 100 hertz. But we definitely have some spread here across all these parameters. In this new build, we're also building up a magnetically shielded room. And that's been quite the effort. And we've had to deal with degaussing the room and trying to keep that magnetic field inside the room low. As you open and close the door, the degaussing becomes an issue and it magnetizes over time. Put a lot of work into that. I don't think I'll have time to address that now, so I'll skip over this, but it's been a lot of work. We've also developed a coil system that allows to control the field inside the room because we have to operate very close to zero field. And so like a 10 nanotesla residual field needs to be canceled out. So we developed a 32 channel coil system. And then finally, a picture of our array as it's starting to come together here. It looks something like this. And this is very Back to the Future looking type device, if you ever seen that movie. And we're getting set up to do some visual stimulus here. So with that, let me conclude. And so we've worked on this person-sized shield and had some nice demonstrations in terms of source localization and this brain-computer interface, being able to get 80% accuracy over 10 sentences. Very interested in moving towards open vocabulary. Right now, we're looking to scale up towards a 72 channel system. And we've done a lot of work on redeveloping our sensor. And we hope to have measurements in the coming months. And just a final thought before I conclude the talk is that it's been really exciting to see the development of this whole field over the last several years. And I've just been honored to, have contributed to these new measurements where we're looking at magnetic fields. We're doing MEG in children with epilepsy. And we're starting to see maybe a real impact of this technology in measuring epilepsy in children. And so, it used to be that they would use these squid machines, but these wearable devices are much better tolerated by children. And that's very important for identifying where the epileptic activity is inside the brain for these youngest of participants and patients. So that's been very exciting to see. So I'll conclude there, and thank you very much for your attention. Happy to take any questions.
Yeah, thank you so much for this fascinating insight into modern quantum technologies. Questions from the audience? Guy.
A quick one. You're at femtotesla. Why are you not already required to have a Faraday cage?
Yeah, so it's what we use is a magnetic shield rather than a Faraday cage. And a magnetic shield is, well, I guess I would say a Faraday cage does not block out low frequency magnetic fields. So you have to use these mu metal magnetic shields to get rid of this background field. And so that's, what I'm drawing here is a, let's see, well, here's a picture of the magnetically shielded room we just installed about 2 years ago. And it essentially already is a Faraday cage, but with the added benefit of having high permeability materials that prevent external magnetic fields from getting inside.
Okay. There's a question in the chat.
I'm not seeing the chat. Yeah, if you could.
Okay, have you considered use math numbers for visual stimuli rather than vocabulary?
Yeah, I mean, we've just started getting into the this area of BCI, and the auditory stimulation was the kind of our first attempt at this. But there's no reason you couldn't try to use a brain-computer interface with auditory stimulation. There's already been some work in this, quite a bit of work in this area, actually, using squid systems that have shown, actually fMRI systems that have been able to show really amazing results of decoding over, I think, thousands of different stimuli, being able to decode thousands of different images that people see. So it's definitely a real thing, and something we'd be very interested to work on.
Would improving the spatial resolution with the new generation or the new version of the technology improve the confusion mix in the decoding of the sentences?
Yeah, one of our motivations for going to a full head array is that you just get more information out of the brain. And if you're able to, I mean, we're kind of measuring the auditory cortex, but if we can measure more of the frontal cortex, there's been some literature shows that if you can measure more frontal cortex as well as the auditory cortex, you can reduce that confusion matrix, and so we'd be excited to do that. Yeah.
I think there's a question from Phil Marston.
Yes, my question is, can you remind me what is the frequency of the modulation magnetic field, and how did you pick that frequency?
Yeah, so our modulation magnetic field, we set it at 1 kilohertz. That's kind of a nice round number that's nice for the human mind to wrap itself around. But let's see, the reason for that is that frequency is you want to be high enough frequency that you're outside of your measurement bandwidth. So the human brain responses are, you want to measure kind of up to 80 hertz or so. I mean, there are some brain responses that get up into the few hundred hertz regime, but most of everything we want to measure is between, say, 2 hertz and 80 hertz. And so we do lock-in demodulation, right? So you always need to lock in a low-pass filter with that lock-in demodulation. And yeah, so we're talking about this modulation here, where we're defining the sensitive axis. And but you also don't want to go too high, because the higher the frequency is, the larger the magnetic field that you'll be applying. And then if your magnetic field is too large, you'll start to get out of the surf regime, and it'll cause extra broadening.
Okay, thank you.
Sure.
Good. Do we have any further questions from the audience? Yeah, one over there.
Not strongly related to physics, but you mentioned this device has a better resolution in thermal detection or something like that. I'm just a little bit confused. Like why should we also focus on the thermal detection part?
In terms of resolution, I was just talking about the spatial resolution, and so that's that argument about spatial resolution was here, where you can get closer to the brain, and because you're closer to the brain, you're able to get more spatial information about the magnetic field map around the surface of the head, and therefore get improved spatial resolution compared to the surf magnetometers, which have a standoff due to this cryogenic insulation. So maybe I misspoke at some point and said thermal resolution or something, but I mainly meant spatial resolution.
All right, any more questions online? If so, please speak up. I don't see any. Well, then maybe let's thank Peter again for a fascinating insight into the quantum world.
Yeah, thank you.